Good morning. Welcome back to Data Structures in Computer Science with Cody Henriksen. We're looking again with C++ to explore data structures. We're continuing on with our linear data structures, specifically looking at the idea of a circular list. Circle? Linear? What? No. But if you take a circle and you unwrap it, and so we have our front and an end and just pointing together, it's a circle. I know. Crazy. But here we are. We have our quick little UML diagram to take a look at how our structure itself works. Just a quick little basic structure. Again, we have our abstract base class of list of type. I made a small bad design decision where originally was going to have linear node become my double node, and I made a change, decided not to use it. So I have these two not so helpful methods for CircularList of getFront, getEnd that we're not going to be using it also. No big deal. We won't touch those. But we still have CircularList, which uses public inheritance from that abstract base class. So all of those methods are implemented. We also, of course, add a constructor and a destructor for the class. And of course, those two methods we're not using. We also have a private helper method, findNode, which is where we're going to actually save some time and provides more efficiency that a regular linked list doesn't have available to us because it only works one direction. We, of course, have our node of type, which is that base class at which all these components are stored from. And it has a data member called data. I know, crazy. And of course, the getters and setters that belong to that. We also have our double node. This is what's going to be building our structure, our linked list of double linked list, aka circular list. And it has a pointer for next and a pointer for previous because it's going to go back or forth through our structure. We have our constructor with no parameters. We won't ever use it, but because of the fact we're using C++, it's always a great idea to have a constructor that takes no parameters just in case we ever have to put some default data member in there. We can construct that immediately. We have our constructor takes a type parameter, which is the one we're going to be using most often, and as well as our constructor takes a type, a pointer, and another pointer, so it can refer to the actual structure. We can build it and link it at once. Then, of course, we have our hashtag basic methods for getSet. For next and previous, and those are really basic as well, but we don't have to worry about that. We've got them right here inside our UML diagram. Let's go ahead and let's take a look at our structures organization. So I'll go to my navigation window inside Xcode. As we can see here inside Xcode, I've got my nodes thing. We'll take a look at the double node class right here, and we're only using header files because this is a templated class. So we'll scroll up here to the top so we can see our class file right here. And in our double node class, we have our class definition. Because this is templated class types, we can make it so to work with anything. We have our template class type definition at the top of our class. We have our class name of double node and using public inheritance to refer to node of type. Because, of course, that's obviously a separate file, we have our hashtag include node of type up here in our implementation section. In our protected, again, we have our pointers for previous and next. And again, we just give it right here, double node of type pointer, because that we can make it for any kind of structure we can simply create in C++. Easy peasy. In our public section, however, we have our three constructor prototypes. And again, a prototype, we simply have the name of the method itself or constructor, followed by a semicolon, and any parameters that we have with that. Now, we don't have to give a variable name for our parameters like I've done here, but I find it makes it a lot easier to read and make sure I have a good name, so I plan it out in advance. So I always make sure I put my data members with my parameters with a name on this as well, even though it's not required for C++ compilation. And so our basic constructor, our constructor with a single parameter, and our constructor with three parameters so we can link our project in place. We have our hashtag basic methods for get previous and get next, as well as set previous and set next, passing them pointers so we can grab that for it. Let's scroll down a bit and let's take a look at our constructors first. We can see our constructor information is really easy. We have our template class type, of course, that help of every single constructor that we're using for this because everything we're making this has to have a type attached to it. And when we have that little type, that little gang sign we're using to actually refer to constructing these things, this tells us what we're building it for. And so we have to have that on top of everything we're working with. And so we have our constructor. It tells that the class itself is a double node of type. Our scope resolution operator, the double colons, so we can say what we're belonging to. And this is then our constructor call itself, double node parens. Then we use the single colon to show what we're calling our super constructor, in this case node of type, and we're not passing information, so no big deal. That will, however, build everything that needs to happen inside node as well. Then we have our two data members that belong to the double node class, previous and next, and we assign them default to null pointer. No biggie. Our more common constructor, again, template class type for everything, the scope resolution indicating it belongs to double node, and then the actual constructor right here has type data as a parameter. Now that we're in the actual explanation of our constructor, we do have to have a data member here, or a parameter name here. And that parameter name right here, data, becomes the actual parameter we're sending to the superclass constructor of node right here. So this actually then goes to node and calls the node constructor with this data parameter. We've already seen that before, so we don't have to relook at it again. But again, with this constructor, we don't know what pointers we're linking it to, so we automatically initialize by default our previous and next setting to null pointer. Our more powerful constructor, this one right here, takes the type data and then a pointer for previous and next. And by using this, I said this next is next and this previous is previous. So I can attach these individual ones right here. Now, as you can see right here on my actual code, my pointer operator right here is before previous. On this one, it's after DoubleNode type. And again, it doesn't matter where we put that. I can also leave it right here with a space, which is where I actually prefer it, but it doesn't actually matter inside C++. So whichever one is your comfort when you're actually just using a parameter, it can be anywhere on that. So we have that right there. And so those are our constructors. Really easy, pretty simple to do. Let's take down and look at our getters and setters. Now these are hashtag basic, of course, but as you can see inside our getters and setters, it works just like every other getter setter we've written in C++ or Java, or even Swift for that matter, where we have the name getPrevious, and it returns the associated data number previous. Get next, next, and set next. Look, this selector next equals next. Looks a lot like Java. So our getters and setters are really basic. They look the same because they work the same. They're simply really simple operations. And of course, because we're using a templated class, we end all of our definition with the hashtag endif. That says the class definition of DoubleNode is over. And so our DoubleNode is what we're using to construct the actual structure of that list. So we'll use a whole bunch of these to actually put it together. Let's go ahead and take a look at the actual implementation of the list itself. So first, let's take a look at our abstract base class, in this case list. And as you can see right here, we have our list class. It uses the hashtag include assert and a link to linearnode.hpp because that's the structure we're working with. As I said earlier, I made a small design decision where I was incorrectly using a linear node because I thought I'd be building that structure for all my things and using linear node for everything. And then looking at the structure when I redesigned my code, I realized that linear node would not make a good base class for DoubleNode because of the idea of having to do a lot of force casting, and it didn't make sense. So this design decision was a poor one. I shouldn't have had that get front, get in right here. Bad choice, but no big deal. We'll take care of that later. And so we're going to have a couple useless methods we'll be working with. But we have our addAtIndex, remove, and getFromIndex that we're going to be using all the time, as well as our getSize, because that's kind of a big deal in a data structure. So we've got that right there. So let's go take a look at CircularList.hpp. And again, hashtag if and def, we always have to have that for all of our templated classes inside the header section. So we have that right there, it's defining this. And again, what goes after the hashtag if and def doesn't really matter as long as it's unique throughout the project. So we just want to make sure we keep that nice and simple. And so using the file name and changing the dot to underscore really makes it simple. We of course have to link back to our abstract base class because we're inheriting from it right here. And of course we have to hash include to DoubleNode because we're using that for our structure. So those hash includes have to be inside that. And because list has assert attached to it, we don't have to include it here. We've already got that hash included. Again, template class type goes at the top of everything. Because we're doing templated class types, that's also why we're doing a .hpp. As you see throughout this project, we don't have any CBP or any implementation files in this because the actual implementation, the code for that, the .o file for it, gets generated for that upon compilation when we're actually using this. So if I'm making a templated class of int, it generates the .o for that, for the int for that one. So I can actually use it as needed. And that's what the power of templated classes are inside C++. So in our private section, we have our private data members of front and end because we're not going to be worrying about having to inherit from that. Those are just DoubleNode pointers of type, and we have them right there. And then we have also our private helper method of findNode, which returns a DoubleNode pointer of type. And again, with all prototypes inside our class definition, we just end it with a semicolon, and I give it a nice little name because I know exactly what I'm doing with that. In our public section, we have our constructor and destructor. Basically, every single thing that we do in C++ needs to have both of these, especially with data structures, because we're dynamically allocating data. So we have to have a destructor for that. We have our required methods for our class. And so we have addAtIndex, remove, getFromIndex, and getSize, ones we're going to really be using. And there are two unused methods that, because I changed my design of my structure, I'm not using anymore. So I have linear of type pointer, getFront, getIn, that are just going to implement with nothing inside them. It's fantastic. So let's go ahead and take a look at our constructor. As you can see my constructor right now, I'm going to set my front and end to go to null pointer because they don't point to anything yet. I'm simply just creating my brand new list with nothing in it. It's amazing. But my size, we do a default initialization of 0 because we don't want to make sure we accident link to some other int value could possibly be stored inside that value in the data structure. So we force that size to be 0. And since that's included from list, we have to use this selector size. So we can refer back to that data member belongs to the class itself. So we've got that right there. So we can refer to that. It's in the protected section. So we can go over there. Let's go take a look at our destructor. Our destructor is a much more powerful thing. We have to actually make sure we go through and deallocate all the memory that we're working with when we're using a circular list. And so again, we use the tilde to indicate that it's the destructor. And I'm going to create a pointer reference to talk to current, assign that to be front, and then I'm going to set, as long as front is not pointing to null pointer, or is equal to null pointer, excuse me, I'm going to set front to be front's next, and I'm going to delete current, that pointer I just created, and then assign current back to front. So I can move pointer all the way through my circular list, all the way around until I get to end again, which then would point to null pointer, which at that point I'm done destroying all my memory allocations. Easy, regular go, works just like a list one. Made it really simple. Let's go ahead and let's look at our next set of methods. So we have our add method. Our add method has a bit of work attached to it. Inside our add method, it takes a type item as a parameter because we're automatically just be able to add to this. And I'm going to then create a DoubleNode pointer called addAtIndex. And then I'm going to check to see if my size is 0. Because when I'm first creating this, I have to actually make some changes to this. So first thing I have to do, I'm going to say addNode is a new double node of type, pass an item, which we'll call then the DoubleNode constructor, build all that information up, and then I'm going to go and say that this selector front is going to be that added node. So I create that reference so I can put front to point to this. If I'm not the front one, I'm now adding to the end of this. And so I'm going to say addNode is new double node of type, and I'm going to pass it item. I'm going to pass it the end of this, and its next one will be front because it's going to make that circle, so it's going to keep adding to it. So my new addAtIndex already knows who its previous pointer is, the previous end, and who its next pointer is, which is the front one, because we're going to build that circle all the way through. Then I'm going to set end to set its next node to point to this new node that I just made it addNode. And now, after I've created those connections, the last step after this is going to set to this selector end. I'm going to have that point to addAtIndex because I have to move in now to point to this new node I just made. And I want to make sure I do this after I actually add because I have to make sure I make those proper connections so I can build that. A nice way to look at this is if we look at the idea of using a barrel of monkeys. So barrel of monkeys have a previous pointer and a next pointer. And I make sure I take this next pointer and I attach it to the previous pointer of this monkey. I take this next pointer attached to the previous pointer of that monkey and so on. And I can wrap those around and I can make that lovely circle right here. Oh. But with monkeys, not too easy to hook them together. Maybe some other chain type toy would be really nice to show up, but we can actually show how those connect together. So barrel monkey is a great way to play with this and actually get some of this information. So after I've made that connection to move into added node, I of course have to make sure I set size to go up by 1. And in this case, I'm using this selector size ++. Easy, ready to go. Let's take a look at our next method, the addAtIndex. Our addAtIndex is a little bit more complex because when we're doing that manipulation of actually adding a specific spot inside a double linked list, we have to have take a bit more information and put it together. Of course, it's templated class type. And as with most of our structures, we have to do the assert on that because we have to make sure their index is a valid index. And in this case, we have to assert the index is greater than or equal to 0 and index is less than or equal to size. Because if I'm adding its size, I'm just adding to the end of the list. So it's totally okay to do so. I then have more pointers I have to actually work with because when I'm using the addIndex, I have to actually manipulate things. And so I have a double node pointer previous, next, and addMe. And those are the ones I'm going to be working with. First thing I'm going to do is I want to check to make sure if my index is less than size. So if my index is less than size, I need to actually find my node and actually do that. And so that's where I have this lovely little findNode call right here. Oh, a new method. And so I'm going to say next equal findNode. So let's go take a look at that method right here. So in that findNode, I want to go ahead and take a look at that. So I'm going to use my ability to use the navigation inside Xcode to do that. So I'm going to go over here and I'm going to scroll down to my findNode method. And so I have up here, I have the definitions in my prototype section, the actual implementation down here. So I'm going to go down to my definition. And my findNode method, we're going to use this to make it so we can save some work in our code. Now here I have my findNode method. My findNode method returns a pointer of double node of type. Now in this case, I'm only worrying about this if my index is less than size because my assert is taking that because when I'm finding node, I'm making sure it's going to be valid. And so I have to make sure that I'm looking inside the list itself, so I have to make sure it's less than size. Different from what I just saw earlier inside my addAtIndex. Then I create a new pointer called nodeDefined. Notice that I don't assign equal new because I'm not reallocating memory for this. This is just a pointer I can look at and point to something. Then I'm going to check to see where my index value is. I'm going to check to see if index is less than size divided by 2, otherwise. So if it's less than size by 2, I'm going to assign it to front. If it's not less than size divided by 2, I'm going to assign that node defined to be in. So I'm going to start at one of the either ends of that circular list, or if I was doing this in a straight linear list, either one like this. Then I'm going to go and either go forward through the list or backward through the list until I find that actual spot using a regular for loop. And so I set position equal to 0, position is less than index, position goes up by 1, and my node defined gets moved to each next one. So after I go through it, I'm going to move to the next one, to the next one, and I use that less than, so once I get to, as long as I'm less than index, I'll keep grabbing it, and when I get to that value, where I'm index -1, my node defined, when I grab its next, aha, index, I grab that correct one. Same thing when I'm going backward. So again, if I'm looking through my list of monkeys, so with my findNode method, I want to actually take a look at this using some monkeys so I can actually see what we're doing with this. So I have my index in this case, I'm going to pass it 2 as a parameter. So I'm going to go 0, 1, 2, because that's obviously less than half my list. Great. So index is less than size divided by 2, so I'm going to go into that first if block on my structure. Node defined is pointing to front, which is this node right here, the monkey I'm holding with my hand. And I'm going to say for int is the position is 0, position is less than index, position ++. So 0, less than index, sweet. So I'm going to go node defined is going to point to node defined get next. So I'm going to go to its next, which is right here, 1. Okay, Great. 1 is less than 2, so I go to the next one. Node defined is equal to node defined get next, so I'm now pointing to this one. 2, I have not, node 2 is not less than 2. So I don't go into that loop. I can't go into the else because I failed that test. So now my node defined is pointing to the index I'm looking for, this little orange monkey. Now, that pointer now refers to this node, so I can actually find this. The same thing works from backwards. If in this case I want to pass it 0, 1, 2, 3, 4, 5. Okay, 5, my first purple monkey. Fantastic. So pass it 5. Okay, 5 is greater than half. Fantastic. So I'm going to start off at end, pointing to this monkey. And this is position size -1 right here. Position is greater than index, okay, which is 5. So I'm going to start off at 5 minus 1, so 1, 2, so 0, 1, 2, 3, 4, 5, 6, 7. Okay, so 7. So size -1, position is greater than index, position minus. So 7 is greater than the value. Okay, great. Position minus right here. 6 is greater than value. Go up again. 5 is not greater than value. I get out of here. So that points to the previous one right there. Okay, so I can actually grab this. So this lovely little helper method of findNode lets me cut the time in half of looking through it. So I only have to look through half of the possible monkeys to find my value. So that circular node, nice little linear search, really saves some time that I can actually do stuff with it. So that node defined method, or my findNode method, excuse me, lets it so I can actually find things for that, and it makes things a lot nicer. So let's go take a look back at addAtIndex and how we are actually using that. So we'll scroll back down to addAtIndex. And again, shrink my font down here. And so my addAtIndex, once I've found that node, I'm now pointing to that new node. So I have my lovely next pointer. So we have my list right here. And I'll point to my little orange monkey. And so my next is that node that I'm looking for. So it's less than size. So this is the node I'm pointing to right here. And we'll put it inside this. Okay, so I'm adding it this spot. So my next is this node. This is going to be my next node. And my previous is next gets previous. So it's this one right here. So here's my one that I'm working for. Here's the next. And now I've got this. I'm going to go down to my addMe because I passed the if, so I can't go to else if. I'm going to go to addMe. I'm going to make a new node. Go to purple because purple is a great color. addMe is a new node. It's a new DoubleNode. And I'm going to pass it so that my item, the value itself, I'm going to have it pointing to previous, is its previous monkey, and its next is pointing to next. And that makes these connections right here and here. So those connections are now made. Now I have to say, is index 0? Nope. And index is equal to size? Nope. So now I have to tell its previous. I have to set its next to point to this one. Because I made this connection for this monkey to talk to here, but now I have to tell the previous monkey to talk to the addMe. And I have to tell next to also talk to addMe. And so that's what those two last lines, 108 and 109, do. And of course I have to make my size go up by 1. That same structure happens for if I have other cases. So otherwise, if I'm adding at the end, I set next equal to front, my previous equal to end, and I still create my new addMe node, because if I'm adding to the end of my node, plonk, 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 adding right here to the end. Okay, so next is going to be front, previous is going to be end, and I go right there. If I'm going to addMe in index of 0, if I put at that 0 spot, I tell my front to point to this new node. And again, I have to tell its previous, the one that I was creating, that I had originally, because previous is going to be less than size. My previous is set to node, my next gets previous. So whatever that one that I'm grabbing, that findNode at index, which in this case it was 0, it's right here. So its previous would be that one right there. So I already have assigned the value, and I can assign that right there. And that's really pretty easy what we're doing with that. Throw some monkeys on the floor, no big deal. Our next method, getFromIndex. GetFromIndex, I'm going to go ahead and use the assert command, making sure my index is valid. When I'm getting from index, I have to make sure that I have a valid index that is between 0 and size -1. So I have to have less than this selector size. That's the only way I can do it. I'm just going to go ahead and grab that lovely index, get the node that's at that spot, and then return holder selector get data. Really pretty easy. That's actually a really simple one for that one, because it's just going to, all the work is happening inside findNode. And I've already cut that work down. Great, don't have to go over it again. With my remove method, as you can see right here, takes an index parameter. Of course, we have to make sure that the size is valid, both greater than or equal to 0 and still less than size, so I can't remove from an empty list. And the reason, again, we have to have these assert statements is because C++ is not that smart. It will access inappropriate memory locations all the time if we let it. So we have to make sure we force our program to do this. This is how we can avoid having null pointer exceptions, but by doing it inside our project itself. So we have our DoubleNode pointer removed. I'm going to set that to be findNode of index, so I actually go to that spot. My pointer remove previous is going to get the previous one from that, and the next to get that after that. So I'm going to get those monkeys out of the list. So my pointer points to this one, and I have my removed is this one I want to find. My remove previous is this one. My remove next is this one. And I could have as many nodes as I want above or below this because it doesn't really matter. If my index is 0, I have a special thing I have to handle because I have to actually make sure my front is pointing to this, because I have to set move to front down to here, okay? Because if I'm moving that, and this end is going to be set next, passing it that. If my front is set to size -1, I have to handle that stuff right there. Then I go ahead and move my pointers around. So I set my remove so if index is 0, I have to have my front point to this next one, which is this one. So I'd have to move front down to here. If my index is equal to size -1, this one down here, I have to move my end to this one right here. And then I have to move the associated front end pointers to go along with that so I can move those around. But the big thing is to set my remove previous, its previous value, it's set, it gets moved to this one. So I'm going to grab this one right here and move its next right here. And this next, its previous, is going to point to this one as well. And now this one thinks it's talking to here, but we're not actually doing anything with it because it's just this one I'm looking at. And so my value, I'm going to grab its data out of here before I do anything with it. I'm going to set my size to go down by 1 because I've taken something out of the list, and I'm deleting this. It's out of the way. And then that value I took out of it, I can then remove. Excuse me, I can then return. We have our findNode. Now our findNode is going to go through, we already looked at that, it helps me find my nodes in there. We've already taken a look at that. We're going to use that, like I said, in remove. We use it in getFromIndex. We also use it in addAtIndex. It's a great helper method. And again, all it does is it goes through, starts either the top or the bottom of the list based on the index parameter we supply to it, and goes down through the list to find it linear the fastest way we can because we're building those pointer relationships between them. We have our getSize. It's a const method. Works just like that. Returns this selector size. Amazingly complex right there. And then our bad design code that I put in there, because I had that linear node as my original design choice, I have these two methods. I'm simply returning null pointer because I'm never going to use them. And so they simply return null pointer, and they're useless, and I can get rid of them. And so that's what we're doing right here. And that's where we're leaving off with our constructor.